Case Western Reserve University's Institute for the Science of Origins proudly presents the Origins Science Scholars Program. The Institute advances the scientific understanding and application of the origins and evolution of human and natural systems. The Origins Science Scholars Lectures are presented with the assistance of Case Western Reserve University's Siegel Lifelong Learning Program, College of Arts and Sciences, and MediaVision. It is my pleasure to introduce my friend and colleague Dimitrios Psaltis, professor of astronomy at the University of Arizona and astronomer at Steward Observatory. His research focuses on the physics of neutron stars and black holes, the properties of magnetohydrodynamic turbulence and accretion flows, the testing of the theory of general relativity in the strong field regime, and the physics responsible for the accelerating universe. Tonight he will talk about the work he did as project scientist of the Einstein Horizon Telescope when it took his famous first picture of the black hole. Please join me in welcoming Dr. Psaltis.
Thank you very much, Glenn, and thanks to the Institute for this invitation. It is my real pleasure to be even remotely with you here today to share with you this very exciting project that I had the good, the privilege and the good luck to be a big part of over the last almost 2 decades now. And I'm talking, of course, about this global collaboration in this global array, the Event Horizon Telescope, that took the first picture ever of a black hole in the cosmos. And you've all seen this picture, I'm pretty sure, and I have it here in my first slide. My goal today is to take you to a little journey in time over the last at least a decade about what it took to put together this global experiment, this global telescope and this global collaboration, and take that picture, something that even a decade ago we considered to be impossible, but also a little journey in space to talk a little bit about the galaxy long time ago and far, far away from where the light left 55 million years ago, way before any of us was on Earth. And that galaxy that has that big black hole in the center, and that galaxy sent that light, that image that we captured in 2017, 55 million years later. So it is the spring. And if you go out in one starry night and look towards the south, you're going to see many constellations. And one of them is called the constellation of Virgo. And you can see it here, Virgo the Virgin. And if you have a good pair of binoculars and look between the hands, here the arms of the Virgin, then you see a group of galaxies called the Virgo cluster. We're discussing what do you call a group of black holes. We still don't know, but we know that we call a group of galaxies, we call it a cluster. And if you look at one of the brightest, one of the most massive galaxies in that group, it goes with the name of M87 because it was the 87th galaxy in a catalog many, many, many years ago by Mr. Messier, who was looking at fuzzy things in the sky that people were confusing with comets and said, these are not comets, don't keep on reporting them as comets, as if this was the 87th of them. And when we take a picture of that galaxy now with a really big telescope, or a really high magnification telescope like the Hubble Space Telescope, is what you see is that not only do you see the galaxy, but you see this jet of light that comes out of it. And this is something that we've known for about a century now, about 100 years now, but only in the last 30 or 40 years, we realized that those big, massive jets that we see from centers of galaxies are emanating, they originate from supermassive black holes in the centers of the galaxies. And these black holes have masses that are millions or billions times the mass of our own sun. So people have always been intrigued about black holes. They used to be a theoretical construction, and then we had more and more evidence with observations like this that black holes really exist in the cosmos. But several of us wanted to go one step further and ask, what would it take to take a picture of a black hole? And more importantly, what would you see if you were to take a picture of a black hole? And this is an interesting question, of course, that doesn't have an obvious answer, because a black hole by definition is an object so massive, that has such intense gravity that does not even let light escape. The only way to take a picture is by look at the light of a black hole. And if the black hole is black, what is the point of taking a picture of something black, right? So the first question that we need to ask in this little journey is, what does it mean to take a picture of a black hole? And to do that, I have a little animation here of what black hole really does to the light around it. So what I do is, we say always that black hole is a region of extreme space-time warping. So I'm going to represent space and time as this two-dimensional sheet of paper here. And I'm going to send parallel photon torpedoes. These are rays of light that I'm sending from one location of space to the other. And in the beginning, there's no black hole. So what you will see when I let it go is that light, as we know from everyday experience, just moves in parallel rays. There they are, parallel photon torpedoes. But now I'm going to throw a black hole in the middle of the space-time. That will introduce a lot of warping, and light will still try to go in straight lines in this warped space-time, but because the space-time is warped, light is going to get bent. The trajectories are going to be lensed. This is what we call gravitational lensing, or if you want, extreme gravitational lensing in that case. And in fact, whatever light goes into that neck, into that black hole, will never escape from the other side. And therefore, if I have a black hole in a place where, now we go back, and in a place where there's a lot of light around it, because there's a lot of, say, hot plasma around it, and I go from one side of the black hole and take a picture, the black hole being so black will cast a silhouette, will cast a shadow, a very black depression in front of the surrounding bright emission, and I will see this hole in the surrounding bright sky, whatever happens around that galaxy. So this is the idea. Can we take a picture in a place where there's a black hole and look at its silhouette? Of course, in order to be able to know exactly how to do it and what to do and what kind of observations to do, we had to run a lot of simulations of what exactly black hole images will look like. And I will say and explain in a second why that was important. And that was one of the big problems, because those simulations require us to solve very complex equations of Einstein's theory of general relativity around black holes to see what happens to light around them. And this is something that not only scientists, but also Hollywood producers had to face. Maybe several of you have watched this movie of about a decade ago now called Interstellar, where it showed what a black hole would look like if it is accreting matter from its surroundings. And you'll see that little silhouette in the middle of that kind of thing that we're looking for. But as the producers and the people who developed that picture admitted in an interview with Wired magazine, they said that individual frames of the picture took up to hundreds of hours to render in supercomputers because the computation was overtaxed by the bendy bits of distortion caused by Einsteinian effects called gravitational lensing. And this is something that we also knew for decades now, that these are very, very different calculations to perform. So in order to be able to ask ourselves, what will it take to take a picture of a black hole? We first had to solve the problem. One of the problems that we had to solve is, how do we make those simulations, those calculations quickly in order to understand what will it take to do the picture? And what we did was we actually used some, at the time, modern technology that you can find in each one of your cell phones, in each one of your computers, if you care to play computer games. And each one of the cell phones in each one of the computers have a little separate chip, a little separate integrated circuit that it's called the graphics processing unit. And the only thing that it does is it calculates, it renders the images of whatever your algorithm, whatever your computer game wants to do, and projects them in the screen. That's the only thing that it does, and it does it very efficiently. What we did is we hacked those graphic processing units and put black holes in the middles of space-times, in the middle of the spaces, and then use these extremely efficient algorithms and extremely efficient technologies to be able to see what happens to light near a black hole. And it got so fast that we could do it on a little laptop, no supercomputer anymore, and so quickly that we couldn't type the commands fast enough to control our simulations. So we did the next best thing, is we got a little interface, you can see down here, which is just like your Xbox, where people can control the simulation with their hands. And now we started taking movies of ourselves running the simulations of seeing what the black holes would look like. And this is the movie that I'm going to show you. This is the hand of one of our colleagues, CKHR at the University of Arizona. This is a black hole, and he's going to throw 1 million photon pulses, 1 million photon torpedoes towards the black hole. He is going to initialize the simulation by moving his hands clockwise. There's the 1 million photons that are going in. You see how quickly it happens? It happens in real time. He is stopping it, he's looking at it, he's zooming in. These are the light that went all to the black hole. He's zooming out. And he's doing it all, controlling it with his hands while it's running in real time with a black hole. And these are the kind of simulations that we did. And we not only did we do them on a single laptop, but then we built a supercomputer out of those graphics processing units to the point that we were able to make a really big simulation of what black holes look like. And what we realized relatively quickly was that it was very important to do those calculations, because if we were to look at the black hole in the wrong part of the electromagnetic spectrum, using the wrong wavelength of observation, say radio wavelengths versus infrared versus optical versus X-rays, then whatever is around the black hole that generates that light on which we want to see that shadow cast would be so dense that will actually obscure the black hole. We will just see a big fluffy blob of cloud, as this simulation shows, and we won't be able to see the black hole itself. There's a black hole in the center. This is the material, the hot plasma that sends all that light, but it's so opaque that we cannot see it. And we had to tweak the light of observations such that this material becomes transparent. This is the same exact idea why when you take a picture of your hand, you see your flesh. But when you take a picture of a different wavelength in X-rays, you actually can see through your flesh and you can see your bones. So what we did is we changed the wavelength to the point that the plasma became transparent. And now we can see a little bit of plasma emitting a lot of light around the black hole, and we see that emission of light in its very, very center. And this is exactly how we picked the appropriate wavelength of observation that turned out to be about 1 millimeter. 1 millimeter is 1/10 of a centimeter. A centimeter is 1/2 times an inch. So it's a small fraction of an inch. This is the wavelength of light that we're using, just like radio waves. But there was another problem. The black holes, even though they're supermassive, billion times the mass of the sun, they're also extremely, extremely small in the sky because they're very, very far away. The one that we wanted to look at, for example, in that galaxy M87, is 55 million light years away. So how big is the black hole in the sky? And I can give you the number, I will give it to you in the end, but these numbers are so astronomically small that it's very difficult to understand what it is. So instead, I'm going to try to connect it to something in the sky that I'm sure you've all seen. And this is the moon. So the moon in the sky is about 1/2 a degree. A degree is a fraction of a circle, right? Now, if I take a degree in the sky and divide it by 60, I get what we call an arc minute. This is like a clock. I take 1 arc minute, I divide by 60, I get 60 arc seconds. I take an arc second, I divide it by 1,000, I get 1,000 milliarc seconds. I get a milliarc second and divide by 1,000, I get a microarc second. The size of the black hole in the sky is 40 microarc seconds. And if you do that calculation, what you do is you take a degree, you divide by 100 million times, and 40 of those will be the size of the black hole in the sky. And this is something so small, and just to give you another example, it is the equivalent not of taking a picture of the moon in the night sky, but it's the equivalent of taking the picture of a donut on the surface of the moon in the night sky. Now take your best telescope, take your best camera, take a picture of the moon, zoom it in, and see if you will be able to see a donut. This is the kind of thing, the kind of picture that we wanted to take. Now, we have a wavelength, 1 millimeter of light that we need to observe. We have a size in the sky. Then we ask ourselves, how big a telescope should we make in order to be able to take the picture of that donut on the sky at 1 millimeter wavelengths? And the answer is we need to take a telescope as big as the entire Earth. Now, the National Science Foundation is a wonderful place that supports crazy ideas, but I think we would have a very hard time convincing them to give us enough funding to be able to build a telescope as big as the entire Earth. And I think the rest of the population wouldn't let us do it. So we did the next best thing that we could. Instead of making a telescope as big as the Earth, we put telescopes all over the Earth, and we saved on hard drives every single wavefront of light that was hitting each one of those telescopes. We timed every wavefront at the highest possible accuracy using hydrogen atomic clocks, maser clocks. And then we took all those hard drives and we put them in a big supercomputer and combined all the data to make a virtual telescope as big as the Earth. And that technique is called very long baseline interferometry. And this is the technique that we used.
Great, thank you, Dimitrios. Great first part of the talk. So we do have a couple of questions in the Q&A box, and if other people want to ask questions, please put them in there. So the first question is from Bernice Kleiman, who asks, so you told us how we can take a picture of a black hole, but why do we want to take a picture of a black hole? What are we trying to find?
That's a very good question. I have two answers to that. One usually ask me, why do you care? One is what Hillary said, Edmund Hillary, the person who first climbed Mount Everest. They asked him, why does he go to climb the Mount Everest? And he said, because it is there. So, it's curiosity, right? We wanted to take a picture of a black hole to see whether they're real. But more importantly, a black hole is the place where Einstein's theory of general relativity makes some of its most extreme predictions. This is a theory that we're still trying to understand. We're still trying to see whether it explains everything that we know about the universe. And there's a few smoking guns, especially in cosmology, of things that might not go right. So we wanted to take that picture, and as I will show in a second, to see whether that theory that we know works really well near the sun and near the Earth works equally well near a black hole.
So Tim Campbell asks a question that I remember I asked too when you folks published the first picture. If M87 is 55 million light years away, but Andromeda is 2.5 million light years away, and after all, the center of our galaxy is only a few tens of thousands of light years away, why are you looking at M87?
Very, very good question. So let's compare first with our own black hole. I will say something at the very end. The black hole in the center of our galaxy is 1,000 times closer than the black hole in the center of M87. So it's, in principle, it could be much bigger in the sky. At the same time, unfortunately, the black hole in the center of the galaxy is also 1,000 times less massive than the black hole in the center of M87. So when you project it in the sky, they turn out to have, for complete luck, practically identical sizes. So we actually observed both, but we decided to go first for the one in M87 for reasons that have to do with the astrophysics and variability and all the mess between us and the center of the galaxy. How about Andromeda? Andromeda is makes us very unhappy, because even though it has a massive enough black hole in its center and it's close enough, the black hole doesn't seem to be emitting any light. The material around it doesn't seem to be emitting any light so that to see the silhouette on top of it. Remember, we need something around it to emit light to cast that silhouette. So this black hole, as far as we're concerned, is black on black, and there's nothing to see. I wish the black hole in the center of our galaxy was as big as M87. It would have been observed probably 20 years ago. I wish Andromeda had a lot of light around it, but unfortunately it doesn't.
I'll just ask Mike Weiss's question from the Q&A box. Were the images accurate in the movie Interstellar?
No. And for one particular reason, we actually got into a nice conversation both with the producers of Interstellar and Kip Thorne, who was the famous astrophysicist, Nobel Prize in Physics a couple of years ago, who gave them the equations of how to do it. It turns out that as you see our image, it looks kind of a ring with one side darker than the other. And when they generated it, the director didn't like it. So they started removing physical effects to make it more cinematographic, elegant. And so it is not exactly accurate. The equations are correct. They just removed a number of physical effects, one of them being the Doppler effect, if you know what I'm talking about, that to make it cinematographic, more elegant. So this is where we stopped last time, just to check on the time. This is where we stopped last time, which is we decided to make a telescope as big as the Earth. And the next best thing to actually take every telescope around the Earth that already existed, we're not going to build new telescopes, and outfit them with the proper equipment to combine them together into a big global size telescope. So what that required for about a decade is people in laboratories built the appropriate equipment that goes behind those telescopes. And this is our two colleagues at the University of Arizona. Dan Maroni is professor and Junhan Kim was a graduate student at the time. They're building this wonderful detector to put behind a particular telescope. And actually the telescope that they put it is in the South Pole, literally in the geographic South Pole. So after building it in the laboratory, then they flew first class, as you can see here, with all the opportunities that gives you, to the geographic South Pole, and they installed it in the back of the telescope. They spent actually 4 winters there, for our winters, for southern summers there, and they had some fun doing that. This is again our graduate student Junhan Kim, dressed as a penguin, doing a race that they call Race Around the World, because they ran for a mile around the geographic South Pole, so you can actually go through all the latitudes on the Earth in one single race. But they had a lot of fun, and they put together this particular detector. And then we did it from telescope to telescope to telescope, to the point that by 2016, and doing all the commissioning and testing that was required, we put together this global array. And I will show you a little bit of an animation of this global array and the telescopes. This is the telescope outside of, practically just north of the Alhambra in Granada. This is a telescope, a big array in Chile. This is a telescope in Mexico, in Puebla. This is a telescope in Arizona, just outside of Tucson. These are two telescope arrays in Mauna Kea in Hawaii. And this is the South Pole telescope in the geographic South Pole. So people went to all of those locations, put the instrumentation for each one of them. And when you spread out the Earth into its two hemispheres, you look at the location of those telescopes all around and how they got put together to generate the Event Horizon telescope. Something for those of you that interested about telescopes and how do you make arrays. Unfortunately, as you know, most of the Earth is the ocean, and we need our telescopes on top of mountains. And therefore, kind of by definition, we can only build very sparse arrays as opposed to filled arrays. But we're very lucky that from the location of our galaxies, you can see there are masses, Earth masses all around the Pacific Ocean. So we'd actually make something as big as the Earth, which was just because of the way that the Earth is put together. Of course, telescopes, to make a global array, don't need just telescopes. You need a lot of people to run them. And because the array is all over the world, we needed a lot of people all over the world. In 2012, we put together the collaboration, the Event Horizon Telescope collaboration, and this is the inaugural meeting here in Tucson, Arizona. And the collaboration became bigger and bigger and bigger all the way to 2018. And of course, we have 2020, 2022 are biannual collaboration meetings, to the point that now we're a little over 350 people working on this global array and the observations and the simulations. In the beginning, we were very excited in 2012 because we thought we're going to have something wonderful. 2014 and 2016, we were all exhausted trying to make it work. In 2018, we're very, very happy because the observations had taken place and we knew what the results already were. Indeed, in 2017, April of 2017, almost exactly 4 years ago, we had by far the best weather in the entire, simultaneously in all the spaces, in all the telescopes, from the South Pole, which is in the middle of the night, Spain, Hawaii, here Arizona, in Chile, in Mexico, and all the telescopes turned and looked at those black holes. And I'm here on the right in Cambridge, Massachusetts, in what we call the Central Operations Room, where we were looking at the weather forecast every day and every hour, making sure that everything is working and organizing the whole observational campaign. You might ask yourself, the data were taken in April 2017, the announcement happened in 2019. What were you doing those 2 years? So an interesting part of, before I say that, let me also say that not only did we turn all the telescopes of the global array, but we told all of our friends as well, and everybody who had a telescope that would observe, whether it was in the radio or telescopes in the space, NASA telescopes, everything turned simultaneously to the same black hole to take pictures of the black hole at different resolutions. You mostly see the jet. Only the Event Horizon Telescope can actually see the black hole shadow. But the reason was that we wanted to make sure that when we take the picture of the black hole shadow, we knew what happens to the rest of the black hole itself. But as I said, you might ask, what did you do those 2 years in between? Well, one interesting aspect is that the Event Horizon Telescope generates so much data that even with the best fiber optics connections, it is actually impossible to transfer the data from place to place just electronically. By far the best way to do it is, I will show it in a second. Why is that? Because the data are about a petabyte per night of observing. So in 2017, we had 5 petabytes of data. And the way we do it is we take our hard drives and we put them in crates. Literally, all of those are big hard drives of all the data. And this is the person in the South Pole that we're doing it. And then we put them on a FedEx truck and a FedEx plane. And we send them from place to place to analyze them. There's no way that you can beat the bandwidth of a fully loaded airplane with any electronic transfer, right? You can transfer a lot of data very fast. But what that means is that we had to wait until that following November for the South Pole for light to come in the South Pole, because no plane comes in and out of the South Pole during the winter. So between April and November, we were just waiting for the data to come. Come November, between November and January, we did this high performance computing correlation of all the data of all the telescopes to make that virtual global array. Between January and June, we did a process that's called fringe feeding. Think of it as understanding the properties of the array. It was the first time that was ever built, calibrating it, going through all the analysis very carefully. Between June and August, we converted those data into the images that you saw. And between August and the following April, we were arguing with each other about what's the best way to write the papers and about what's the best way to present it to the rest of the world. That took almost as much time as actually doing the analysis. And in April 2019, we had the first ever publication of the first ever announcement of a picture of a black hole, which very quickly it made it to the next day. It was in the front page of every single newspaper in the world. And the National Science Foundation did a little survey afterwards. How many people saw that picture in the world electronically over the next week? The number that they came up with is unbelievable to me, but I will cite it to you: 3.5 billion people. And if that is true, I think this is one of the most, one of the scientific results that has had the most public outreach in the history of physics and astronomy. And what the picture is our donut. The donut that I was talking before is a lot of light in the vicinity of the black hole. We think that this is this extremely hot, billions of degrees temperature plasma that is coming towards the black hole, is attracted by the black hole by its surrounding material, surrounding region. And at the very center, we have this big depression, this silhouette that the only thing can be, it is aligned with where the black hole is supposed to be. And the only way that we can understand it is the shadow that the black hole casts on the surrounding material. So what we ended up doing afterwards, just to make sure that we got it right, is we used the technology that I showed you before. We did big supercomputing simulations through a lot of material. So this is a cube of one of those simulations. We put a lot of matter onto a black hole, not just photons. And then we calculated, if I had an observer far away that took a picture, what kind of an image would it see? and we developed those complex simulations. And we did a lot of those simulations. We let the weather around the black hole to move around. We let the black hole to have different properties. We let the plasma to have different properties. And we generated a very, very large number of those simulations. And this is a little rogues gallery of some of the simulations that we did. And then we asked ourselves, do the simulations really agree with what we observe? And just to give you an idea, this sender in the middle is a simulation of what the black hole shadow would have looked like if we had infinite resolution, if we could really take a picture with no blurring, nothing whatsoever. Of course, our telescope does not work that well because it has a limitation given the size of the Earth. If the true picture was like that, this is the image that we would have reconstructed. And if you compare it with the real image that we actually took, you see that it's practically indistinguishable. Our theories work, our simulations work, and what we see, this bright ring of emission with a shadow in the middle, is exactly what we have observed in reality. And just in case anybody thinks that this is something that we did after we saw the data, we like to show also papers from several years before the observations happened that do not look significantly different. Of course, the most recent simulations are fine-tuned to the observations, but the general properties of the simulations remain the same. Our theories work when they go near black holes. And I think this is a place that I would like to take another little break, and then we can talk about what did we learn from those observations.
Thanks, Dimitrios. Amazing pictures, amazing work. We have some really good questions here. Let's see where to start. So maybe I'll start with a question by James Lawrence from he asked it earlier. You're saying that you could have gotten a better picture if only your array had been bigger than the Earth, right?
Mm-hmm.
So why not use the orbit of the Earth instead of just the size of the Earth to spread out your telescopes?
Very good idea. Unfortunately, you need to be able to take the observations of all the telescopes simultaneously. And by simultaneously, I mean at the time it takes for one wavelength of light to hit the telescopes, one cycle of light. And the frequency of light is 230 gigahertz, 230 billion times per second. So the only way to do it is if you could put two telescopes far apart in space, and I will say something towards the end of my presentation, and you time tag all the observations to a billionth of a second, then you would be able to take that data and do the observation. But you cannot do like we do for parallaxes. You cannot do one observation now, one observation 6 months later and use that.
Great, thank you. Let's see. So a quick question, Chris Wilmoth asks, how many telescopes are in the array?
So I will show something at the very end. There's more telescopes than sites. So we'd like to say that we have 5 sites, but two sites have 2 telescopes each. So in the original set of observations, we had 7 telescopes and 5 sites. There were a set of observations that just were completed a week ago, and we added 2 new telescopes and 2 new sites. So right now we have 7 sites with 9 telescopes in.
Great. So Lois Goodman has a great question here. Why are black holes located in the centers of galaxies? Do all galaxies have black holes, these supermassive black holes?
Very good question. The reason that a supermassive black hole ends up being at the very center of the galaxy is because, just like with everything else, the heavier object, it's by far the heaviest object in the galaxy by millions and millions of times, will eventually settle toward its center. And when galaxies collide, you get perhaps 2 smaller black holes, they collide, they make a bigger black hole, and when the galaxy settles into something else, the black hole will settle in its center. Do all galaxies have black holes? We haven't looked at every single galaxy and every single black hole. Actually, for many galaxies, we cannot even tell whether there's evidence for a black hole or not in the center. We don't have the capabilities to do it. But as far as we tell, all galaxies other than the tiniest ones have a black hole in the center, or the vast majority of the galaxies other than the tiniest ones have a big black hole in their center.
So I'm going to finish up with one more question that from David Hunt, and we'll come back to some of the others after. Mm-hmm. because it highlights something that I didn't understand at first when I first saw the image. Because you show the shadow, but usually you have a shadow if you think of a shadow if there's stuff behind it glowing and it can't get to you. But presumably there's stuff in front of the black hole too that's glowing. So does the black hole look the same if you could view it from other angles? Would there be a shadow no matter where you are?
A very, very good question. So I threw some things under the rug here when I was discussing it. And remember when I showed the original simulation where I said, if you look at the wrong wavelength of light, you see effectively a cloud. This is the things that in front of you. So you need to pick the wavelengths of light just in the right place, that everything is transparent all the way. So you have the little things in front and behind and whatever, but it's primarily transparent. And the reason that you outline the thing around the shadow is because of intense gravitational lensing that makes the path of light make circles around it, maybe half a circle, one circle, two circles around the black hole, and pick a lot of brightness. So it is really a relativistic effect that allows you to see that bright ring of emission, or this little thing that I show you here, even though all the material that you have around is so transparent that in principle you wouldn't have seen it. It's a little more elaborate, but yes, this is material very, very close to the black hole. What did we learn? And somebody asked, why did we care? And as I said, one of the reasons that we cared is because we are still in the process of trying to understand that theory, the general theory of relativity that Albert Einstein gave us more than 100 years ago now. And so far, until the last 2 decades or so, we have been only testing it where we could, right, in the solar system. We could see what happens to planets. We could see what happens to light that is being sent by spacecraft. This is the Cassini spacecraft between Jupiter and Saturn, and the light that it sends towards the Earth. We could do all those experiments and say, the theory of general relativity is not bad. Actually, another thing that you all have in your cell phones is the GPS receiver, where you are, when you're driving. And the only reason that the GPS receiver is because the corrections that the theory of general relativity tells us turn out to be correct. However, the strength of the gravitational field near the solar system is kind of moderate. It's not very strong. It's not very weak. And 2 decades ago, when we looked at the very, very weak gravitational fields, those of cosmology, we found things that didn't necessarily expect it. Accelerate expansion of the universe, dark energy with a magnitude that nobody could have predicted, and so on and so forth. And maybe this is all okay. You can make small tweaks to the theory and allow it. Or maybe it shows us a much bigger flaw that we would like to look in a different way. Black holes are the exact opposite regime. This is the regime of by far the strongest gravity. And if there is something that doesn't work well, we were thinking that maybe near black holes, if the theory is not 100% right, near black holes, we would have seen a signature of something being slightly different. And what would something be? Well, it turns out that the size and the shape of the black hole shadow, the outline of the black hole shadow, is something that depends almost entirely, and with very, very small complexities, on the theory of gravity. It depends only on what Einstein said. And this little animation to explain to you what we were thinking, this is again one of those simulations that works. As I said, the black hole casts a shadow in the plasma that surrounds it, and that shadow has a very precise size. Now I'm going to get rid of the simulation. Here's a little gauge that tells you whether you are ZR or not ZR. And what we find is when we tweak the theory of gravity and we make the gravitational field being stronger or less strong than what general relativity predicts, then we find sizes of the shadow that are different than what Einstein predicted. Now with the Event Horizon Telescope, not only did we measure the image, and here you see it a little bit blurry for the purposes of the images, but you can actually measure the size of that shadow more precisely than what you see. And what we can do is we can ask ourselves how different from the predictions of general relativity can we be and still get this bright ring of emission to be where we observe it. We know the distance of the galaxy very well from basic astronomy. We know the mass of the black hole very well because we see the motion of stars and gas around it that allows us to infer the mass of the black hole. We don't have 3 parameters. Either Einstein was right or it was not. And what we found is that Einstein wasn't it right, give or take 20%. So this is the predictions of the theory of general relativity were exactly what we measured with the size of the shadow in the M87 galaxy, give or take 20%. And then we went on beyond that. So you might have seen a more recent announcement from the Event Horizon Telescope that not only can we measure the light that comes from the black hole, but we can also measure the polarization of light that comes from the black hole. This is something that you might have seen when you have polarized sunglasses and you look at something reflected from the, from a metal surface or from the window of your car, and then when you move on one direction or on the other direction, you can see the reflected light to be completely black or to be completely bright. There's a particular orientation in light that polarized light prefers to propagate, and that orientation of light tells you something about the magnetic fields near the black hole. So this is how polarized the light that we see in the image of M87, of the black hole in M87 is, and you see this very beautiful swirl that comes through. This is again something that is related to general relativity. This is the gravitational lensing swirl that gives rise to this polarization. And when you go through the analysis, which I won't have time to discuss today, you find out that the magnetic field in the black hole is actually very ordered. The black hole has ordered large-scale magnetic fields that penetrate its horizon, and this will tell us a lot about plasma processes near black holes as we analyze it, as we understand better and better. But the next big thing is more about the black hole in the center of M87, but it's going to be something about the black hole in the center of our own galaxy. And as I said, I've already answered that. This is a black hole that is 1,000 times closer, but also 1,000 times less massive. So it's going to be practically the same type of image in the sky. And the reason that we know it, so this is a beautiful animation from real pictures. This is a composite picture of our own galaxy seen from the Earth. So you see the Milky Way, it looks like a pancake, that's why it looks like that. And as I zoom in, it's in the Sagittarius, the constellation of Sagittarius. As I zoom in through the clouds and the gas towards the center of the galaxy, there's a lot of clouds and there's a lot of gas, and that's what makes life harder for us, which is why we didn't start with this black hole. We started with one in M87. And if I look very, very, very close and take pictures of the stars, these are actual pictures that were taken. Let me go back a little bit before the thing. These are actual pictures that were taken over about a decade of the stars at the very center of our galaxy, and they all seem to be orbiting the exact same central location. This is a model of those stars, and that central place emits no light whatsoever other than in the region around it. That central place has a mass about 4 million times the mass of our own sun. And this discovery was actually the people who did that discovery, Reinhard Genzel and Andrea Ghez at UCLA, got the Nobel Prize for Physics this past October. We know the black hole is there. We know the mass of the black hole. We have actually turned our Event Horizon Telescope to the exact same location in 2017. We have analyzed all the data. We have looked at all the data. Unfortunately, I cannot tell you how it looks like. Stay tuned for some time after the summer, early fall, and maybe a year from now, you can invite me to show you part 2 of this, episode 2 of this story. And unfortunately, I already said the story about Andromeda, about M87, about black hole in the center of the Milky Way. When we looked at every other black hole that we know of, supermassive black hole in the universe, there's no other black hole that we can take a picture with given the limitations of our Earth. So what we need to do is we need to make even bigger telescopes. And of course, space is the final frontier. The only way to do it is to send satellites in orbit, take the observations simultaneously, collect all the data, and send the data to Earth to analyze it. And then the sky is the limit, the space is the limit. The fundamental problem of that is that FedEx doesn't deliver hard drives from space yet, right? We had a really hard time transferring data within places on the Earth. Imagine transferring data from remote locations in space. But 10 years ago, nobody believed that we could do this experiment from the Earth. I will be the last person to tell you that we won't be able to do it in space, from space in the next 10 years. So that will be for episode 3 of this presentation, a decade from now. But for now, I'm just going to leave you with the iconic image of the first black hole in M87. Stop here and take questions. Thank you very much.
As the host, I get to ask my question too, which is, so can you do a sample return mission where you just like they brought samples back from asteroids, you eventually send the data back, on the FedEx truck, or the FedEx.
Very good question. We have a lot of jokes about those things. One is that those missions are not cheap, and it will be very difficult to convince us or convince anybody to fund, billions of dollars worth of spacecraft for an observation that will last for 5 days. This is how long we observed in 2017. Send the data back and then forget about it. I think we're all hoping to wait a little longer until we make it happen, in a more efficient way, and keep those experiments going and taking more and more observations and more results. The best way to do it is actually not to send the data to the Earth, but communicate the data in real time from satellite to satellite. This is what the interferometric gravitational wave observatories in space want to do with lasers, and do the correlation in real time in space, and then just send down the final answers. Of course, what would that require will require very high performance computers on the satellites, and what that would require is a lot of power. So we're actually developing a lot of new technology to be able to do very high performance computing with the least amount of power possible, hoping to be able to then put it in space, do all that calculation in real time in space, and beam down, the results, the much simpler, like the image if you want, or the much smaller results that we need.
Sidhesh Ampar asks, what about the uncertainties in the picture because of resolution? How sure are you about the workings of the theories, and how far away from the event horizon are the theories valid?
Very good question. This is where the 20% came from, in a sense that if you were to take not the image as we see it, as I said, we can feed directly the data as opposed to the reconstructed image that we kind of blurred to remove all the uncertainties. But if you take the uncertainties of the data face value, we actually can, you can say the general relativistic predictions are accurate to within 1% or a fraction of 1%. The reason that we do 20% is because we went through the very complex exercise of throwing everything in the kitchen sink on our array on our telescope, synthetic data, and everything else that we could imagine to see what could have gone wrong, and we wouldn't have known. So the reason that we quote 20% is exactly that. Now, are the theories valid near the horizon? If you believe in general relativity, there is nothing that it leaves to imagination. You can actually calculate everything precisely all the way past the event horizon, even though you will not be able to tell. So if you believe in general relativity, there's nothing left to imagination. If you find anything different, it has to be something fundamental different in the theory.
So let me ask that question a little bit differently. How close to the event actual horizon are you actually probing?
Very good. So this is another thing that we throw quickly under the rug. We call this shadow, the silhouette, the evidence of the event horizon. It's not really the evidence of it's not really the size of the event horizon. There is a place around the black hole where it's called the photon orbit radius. If I send light tangentially to the black hole, the light will come around and make a full circle. It turns out that the shadow that you see is the gravitationally lensed image of the photon orbit, that location where light likes to circle around the black hole. Everything else eventually will go in. And that radius is 1.5 times the size of the horizon for a non-spinning black hole. So when you see that shadow of the black hole, think of it as 50% larger than the horizon of the black hole, and gravitationally lensed a little bit.
What is the natural evolution of a black hole And so if, we're looking at this as it happened 55 million years ago, would it look any different today?
A very, very good question. The black holes classically black holes can only grow in mass by accreting more and more plasma from their surroundings, attracting and accreting more plasma. And the only reason that we can see this black hole is because it's clearly accreting plasma, right? There's plasma almost at the horizon, which most likely will go through the black hole. So the mass of the black hole is only going to increase. So if you could take a picture at different cosmic times of that black hole, you will see a smaller shadow, a bigger shadow, a bigger shadow, a bigger shadow as a function of time. Now, 55 million light years is not a long time for the age of the universe. We're usually talking about billions and tens of billions of years. So even if we were to take the observation a few years down the road, we would make especially no difference. And if we were to see the black hole today, if we were there, it would probably make not significant difference. But in principle, if we can make this experiment with black holes that are further and further away, that we know that they have different smaller and smaller masses, we should be able to see a statistical evolution of the shadows. Smaller shadows earlier, smaller black holes, bigger shadows later.
So Bernice Kleiman has a question that I'll kind of riff off of a little bit. Now that you've compiled an image, what does this tell us about function? And so maybe not just about the black hole, but about the material going around it.
Yes. So one other thing that I didn't point to is the fact that you see there is a little bit of asymmetry in the brightness. The bottom side is brighter than the top side. And if you remember how that jet that I showed you looks like, and maybe I can find it, I have this image. Oh, here we are. So these are the simultaneous images of the jet in radio, and this is the black hole shadow. So it's bright underneath and less bright on top. The reason that we understand it is because of an effect called the Doppler effect. This is the same reason why a siren sounds at a different higher pitch when it comes towards you and lower pitch when it goes away from you. Not only is the pitch different, but also the loudness of the siren is different. And the same is true for light. So what we think is happening is that everything in the black hole is spinning around the location of that jet. So the things that are coming underneath are pointing at really the speed of light towards us. The things that are above are pointing nearly at the speed of light away from us. And therefore, the bottom part is boosted to very high brightness towards us, and the top part is boosted towards high brightness away from us. From that asymmetry, we can learn something about the velocities of the plasma that is moving around. And from the polarization that I showed you later, we can learn something about the magnetic fields of the plasma. And there's going to be a lot of wonderful plasma physics that's coming out of this as we get more and more deeper into the data.
So we have a couple of related questions from Bonnie Weiss-Sokol and from Randy Pelton. Let's see. So one is, why do nearly all galaxies have black holes? And the other is, for those galaxies that have black holes at their center, is it always a single black hole, or are there examples where there are multiple black holes?
Very good. This is one of the questions of active research right now. Why do black holes grow to the masses that we see? Why they're in the center of galaxies, I kind of already alluded to, because they're the heaviest objects in the galaxy, but why do they have the masses that they have? And what is even more difficult to understand is that some of those black holes have masses of billions of times the mass of the sun, and yet we see them at galaxies so far away that we're clearly seeing them just after the formation of the universe, like the first less than a billion years of the age of the universe, and we don't really understand how those black holes are formed. So this is something that we're hoping observations like this, observations of many other experiments in the universe looking at many different black holes will help us understand. But it's interesting about the binary black hole because, as I said, when two galaxies collide, we expect that this is how some of the black holes gain their masses, by having two smaller black holes collide and forming a bigger black hole. And wouldn't it be great to take a picture of that? So there is one source that we looked at. For those of you who like astronomy, it's called OJ287, that has some weird periodicity. It's a black hole in the center of a galaxy. It has some weird periodicity with timescales that with periods that seem to suggest that two big things are orbiting each other. And it has some weird jets. And so we looked at it to say, if it is two black holes orbiting each other, that would be a superb picture. It didn't look that good. We're still analyzing it. Something is different with the black hole. There's many ways to have things moving around and plasma moving around. Maybe the black holes, if they're there, they're too far apart that we cannot see them. But of course, we're always on the lookout for things like this.
The Origin Science Scholars Lectures are presented by Case Western Reserve University's Institute for the Science of Origins, with the assistance of the Siegel Lifelong Learning Program, the College of Arts and Sciences, and MediaVision. For more information on the Origin Science Scholars Program, including a full video archive, please visit the Institute's website at origins.case.edu.